picture one of my favorite waterfalls in the whole world. Let me get the chat up. Anybody been to Iceland? So I need to know right now because I want to go here. So this is actually not a hike that I've been on. This is on my wish list. I used to tell people that I've been to Iceland, but then I'm kidding, obviously. You know what happens though, when you want to go somewhere, you have something you want to do, and then you see somebody you know that's actually, doing it or there. That's what used to happen to me. So I want to go to Iceland really bad. It's beautiful. Sadly, I just follow too many people on Instagram who are like really amazing photographers in Iceland. So that's probably why I want to go. But this is a waterfall. I'll let you try to pronounce that. I think it's Skogafoss, but you can Google it. It's just a really huge, amazing waterfall there. There's a lot of really awesome just terrain and hiking to be done in Iceland, believe it or not. So I just want to show this. Also, we got gases, liquids, and solids all in one picture. Okay, so it's a perfect way to start talking about chapter 8. States of matter. So we've talked about states of matter, solids, liquids, and gases. We're going to look at a couple things very specific about these physical properties. So we're going to look at the level of energy displayed in each state of matter, and then we're going to start to really understand how these molecules interact with each other as gases, liquids, and solids. We're going to look at not forces, not like chemical bonds that hold atoms together. We're going to start looking at forces that hold molecules together. Okay. So there's 3 different kinds of intermolecular forces. Again, these are interactions between molecules, and they're not chemical bonds. Okay. They're very similar to the idea of a chemical bond, but they're not a permanent chemical bond. Okay. So they do require energy to break them like chemical bonds and things like that, but they're a little bit different. So first, though, I want to zoom in on this picture right here, and I want to talk about these 3 states of matter. Obviously, you guys can probably guess, hey, right here, is this a gas, a liquid, or a solid? Just from looking at the molecules spacing. Yes, this is a gas, okay? The middle one, you've got a little more space between the molecules. It doesn't show that they're moving around, but it looks like they're a little bit fluid. This is a liquid state of matter. And this one, you can see the molecules are really ordered and arranged very nicely. This is a solid. Okay. So let's talk about a couple of things. Number one, the amount of energy. The amount of energy associated with each state of matter. Which state of matter do the particles have the most energy? What do y'all think?
I want to say gas, I guess.
Molecules are flying around. I equate this to cars on interstate. They're zooming past each other. They don't have time to talk. All right. So here, the particles have highest energy. A liquid, they're not moving as fast. Okay. They'd be like just driving through your neighborhood. You're still moving, but not as fast. And then a solid, they're vibrating in place. They still have energy, but they're not moving around like they are in a gas. Okay, so these have the lowest. And I meant to write this. I'm going to write K, kinetic energy. Okay, kinetic energy. These have some kinetic energy. All right. So I want you to remember kind of the way the energy is ordered in these particles. Gases have highest energy. Okay, now let's talk about the level of intermolecular forces at play, the level of interaction that these molecules are experiencing. On an interstate, if you're driving down the interstate, obviously you can call somebody on the phone, but do you have time to talk to somebody in the car next to you? Okay, unless you're driving the exact same speed, right? No, normally not, especially on people on the other side of the interstate driving past you. You have no time to talk. You have no time to interact, okay? It's the same with gas particles, no interaction. So they have no intermolecular forces. Or if there is any, it's like super, super low and negligible, okay? Very little intermolecular forces. Liquids, okay, have a little bit more. You can wave to your neighbor as you're going by, right? You can say hi to somebody as you're driving slowly through a neighborhood, okay? So these have some level of intermolecular forces, some interactions between the molecules. And I'm going to start abbreviating this IMF, intermolecular forces. Okay, solids, obviously, they're like sitting next to each other, they're bonded together. So there's a lot of forces at play between particles and molecules that are in a solid state of matter. Okay, so high level of IMFs, intermolecular forces. A lot of interaction between those particles.
Wait, that's for C or A?
As for solids,
Okay.
yes, which is C in the figure. Okay. So keep those things in the back of your mind as we go through. We're going to talk about what kinds of intermolecular forces are at play between particles. But before we do, speaking of states of matter, we know that matter can change between different phases, between solids, liquids, and gases. And we also now understand from chapter 7 that every single one of these processes has a certain enthalpy associated with it. Okay. So don't forget chapter 7. Let's talk about enthalpy. You see all these different descriptive words: melting, freezing, condensation, vaporization. Okay. Remember that you can go straight between liquid and, gas and solid too. It's called deposition or sublimation, depending on which way you're going. But now you also see these color-coded statements in the parentheses: heat absorbed or heat released, okay? So somebody remind me, when we're talking about a reaction that releases heat, it releases heat. If you're doing it in a test tube, it would feel warm to you. You would feel that release of heat. Is that exothermic or endothermic?
Exotherm.
Exothermic, okay? So if heat is released, I'm going to write this up here. Equals, well, I'm going to move it over. Exothermic, okay? If heat is absorbed, this is endo, okay? Now, exothermic, is this a positive or a negative delta H?
Negative.
Negative delta H, that's right. Okay, so this is a negative delta H, and this is a positive delta H if it's endothermic. So we can actually assign a change in enthalpy to every single one of these processes: vaporization, condensation, melting. Why don't y'all go ahead and do that? Anything that's color-coded red, it's absorbing heat. So this is going to have positive delta H. Positive delta H. Anytime you're moving from a solid towards a liquid or towards a gas, you have to absorb heat to do that. Okay, so that's endothermic. Anytime you are going from a gas back towards a solid, you're releasing lots and lots and lots of heat so that the particles and the molecules are slowing down, and interacting more and more and more until they're touching. Okay, so these are all negative delta H. Negative delta H, all exothermic processes. Okay, so if I ask you on a quiz or on an exam, is this process, melting or blah, 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 or, I might describe the process. Is this exothermic or endothermic? Does this have a negative delta H or positive delta H? You just look at this figure and you can tell me, okay? Keep that in mind. Positive delta H.
Wait, can you repeat that when you said if something is moving towards something, it's
Well,
over?
if you are going from a gas towards a solid, so you're condensating, you're condensing, or you're freezing, you're releasing lots and lots of heat so that the molecules are slow. Heat is energy, okay? They're slowing down, until they're touching. All right?
Right.
Does that make sense?
Yes.
All right. So there's this slide. So we talked about energy, we talked about intermolecular forces. Now we're going to define 3 very specific types of intermolecular forces. Okay, I'm going to scroll to the next slide. Everybody good? All right. So you see that same picture here. Between these states of matter, we've got intermolecular force. So the first type we're going to talk about is called van der Waals. It's also got a second name that it's very, very commonly known as, and I'll use both interchangeably. They're also known as London dispersion forces. Okay. This is the weakest kind of intermolecular force. We're going to talk about it in detail in a minute. The next kind we're going to talk about is called dipole forces. This is kind of the middle strength kind, a little bit stronger than van der Waals, London dispersion, but not the strongest. Okay, but first, what is a dipole? Anybody remember what a dipole is? When does a molecule have a dipole?
Isn't it when it's in equilibrium?
Symmetry.
Keller. Thank you, Rachel, in the chat. Rachel said it, when it's polar, okay? So remember, if you have a molecule like HCl, you got to think about the electronegativity, okay, that electronegativity chart. When you can assign a partial positive and a partial negative, and there's no symmetry, it doesn't cancel, that molecule has a dipole pointing towards because this is where all the electrons are, okay? They're over here, and that chlorine we know has a bunch of lone pairs. So for sure, all the electron density, the electrons in this bond between hydrogen and chlorine are pulled towards chlorine. So we got a permanent dipole. So when a molecule's polar like that, it's going to have what we call dipole forces. But again, we'll define that here on a slide in just a minute. Last one is going to be called hydrogen bonding. Some of you have heard of hydrogen bonding before. What do y'all know about hydrogen bonding?
It's weak.
It ain't weak. It's the strongest one. FON. It can only bond to the, oh yeah. Yes, Molly, fluorines, oxygens, nitrogens. Those are the important elements when it comes to hydrogen bonding. We're going to talk about that. So hydrogen bonding is the strongest, okay? Hydrogen bonding is a important part of why water is a liquid on Earth, okay? At these temperatures that we live in. So unless you go up to like the Arctic, right? I'm going to skip over this slide because I want to start with van der Waals. So they're kind of out of order. Sorry for that. Let's scroll down here to van der Waals. We'll go back up to dipole. I want to start with the weakest, go to the strongest. Okay, van der Waals forces, also known as AKA London dispersion forces. These occur in all molecules. Every single molecule experiences London dispersion or van der Waals forces. Okay. They are dominant, though, molecules for which these are the strongest force in nonpolar. Okay, so think about it. A nonpolar molecule, it's not going to have a permanent dipole. Likely, a lot of times nonpolar molecules are not going to have hydrogen bonding, the capability to hydrogen bond. And so van der Waals forces are the strongest in nonpolar molecules. A lot of molecules like this down here that are just carbon and hydrogen, where all the bonds are nonpolar, because carbon-hydrogen bonds are never polar, okay? They're the weakest, though. When you compare it to dipole interactions and hydrogen bonding, they're the weakest. They're not very strong, but that doesn't mean they're not significant, okay? Maybe it would not be significant if you were just considering two molecules interacting and one single London dispersion or van der Waals force, but across millions and millions of molecules, okay, they can add up and they can have a significant impact on certain properties like melting points and boiling points. We're going to talk about that. They are caused by interactions between temporary dipoles. All right, this is kind of confusing. What is a temporary or a momentary dipole? It's a dipole that just lasts a moment. All right, it's a dipole that's very temporary and it's there and then it's gone. It's not like a permanent dipole in a molecule that's polar. So I want to look at this picture over here. You've got these molecules down at the bottom. These are polar, okay? But these molecules up top, they're not color-coded, so these are nonpolar. We call this rainbow color coding stuff sometimes an electronegativity map. And it's just showing you which side of the molecule has more electron density and which one's kind of which side of the molecule electron poor. But we don't have that. But however, in nonpolar molecules, we know that electrons are never static. They're never just sitting there nicely, okay? Like my 2-year-old, she's never just sitting there nicely. She's always moving, okay? And so we know there's electrons in these bonds right here, right? We draw them sitting there nicely for our purposes, but they're never sitting there nicely. They're literally moving all over the molecule, okay? All the time. So at any given time, here's what you can see. At any given time, if you took a snapshot of this molecule and you froze the electrons in that picture, the electrons, sure, they may be over here. They may both be over here. And if that happens for that split second, for that moment, yeah, you can assign a partial negative and a partial positive to the molecule, right? Okay, because the electrons are on one side, but it's just a moment and then it's gone. But if this happens and if this lines up across molecules, millions and millions and millions of them, you end up with these temporary dipoles that are there and then they're gone, there and then they're gone. Okay, and so if that happens again, where the electrons are on this side of the molecule, then you got a positive, partial positive and a partial negative. Sorry, I'm doing this all in red. I really should be doing it in different colors. Partial positive in blue. So think about that. When you've got a partial negative and a partial positive close to each other, you've got a temporary momentary dipole. Okay, and that's where the interaction for this van der Waals forces London dispersion happens. But because it's so quick, that's why they're the weakest. Okay, and they're just not very strong. All right. So this is moment lasts a moment, and then it's gone. All right. Next point is blank atoms have more electrons. Oh, larger. Okay. The larger the atom is, or the larger the molecule is, the more electrons there are. So the more movement, and the larger those London dispersion forces can be. Okay. So again, larger atoms, more electrons, more fluctuation, more potential to have London dispersion forces or stronger London dispersion forces. Molecules with larger surface area will also have more London dispersion interactions. Okay. So I want to look at this example on here. And what do these affect? Why do we even care about these? Well, like I said, they affect different properties of molecules. So they affect things like boiling points, melting points. And we're going to look at an example in this figure here. I believe this is right from your textbook. We have two molecules with the same, I'm going to use this word, I'm not sure I've used it before, empirical formula. An empirical formula just means it has the same number and types of atoms. Okay, so for example, how many carbons and how many hydrogens are in each of these molecules? They look different because the Lewis structures are different, but we've got C5H what? I think it's 12. Yep, C5H12, both of them, C5H12, okay? So they both have the same number of carbons and hydrogens. It's just that they're arranged differently. So if we look at pentane right here, this is the common naming of it, okay? Pentacarbon, I don't even know what 12 would be, dodecahydrogen. We can call it pentane. If we look at pentane right here, it's kind of all elongated, right? The carbons are just all in a row. And so this one has more surface area, okay? Because it's, the molecules are kind of spread out because of the way they're bonded together, because of the Lewis structure. But if you look at this one over here, wow, we've got a very different name, 2,2-dimethylpropane. Don't worry about the namings. It's kind of all, if you look at this ball and stick model, you can see it even better. It kind of all wadded up, right? Less, so this has less surface area, right? Not as elongated. And then I want to point out something really interesting. Look at, it says BP, this stands for boiling point. Look at the difference in the boiling points, okay? For the molecule pentane that has more surface area, the boiling point is almost 20 degrees higher, okay? It takes a lot of energy to raise the temperature of this substance to get it to boil, okay? Anytime you're raising the temperature of something, that's energy. So it's going to cost a lot more energy to cause molecules of pentane to break apart and boil or melt than it would for 2,2-dimethylpropane. Now, why is that? Well, it all goes back to this point up here. The more surface area, the more opportunity for those electrons to fluctuate and create London dispersion forces, okay, to be on one side of the molecule or the other, to create a temporary, momentary dipole where it interacts with another molecule and there's a interaction there that costs energy to break apart, okay? Does that make sense to everybody? Okay, so I'm gonna, by the way, as we get ready and closer to exam 3, I'm gonna post that recommended list of textbook problems for you to kind of spend some time exercising and thinking through these concepts. I'm probably going to pick a few to work on the reviews Wednesday and next Monday as well. But I'll put some questions to kind of walk you through some van der Waals stuff on that list. But anyways, that's van der Waals forces. So I'm gonna scroll back up now and go to dipole forces, okay? So dipole, all right, look at these. We got polar molecules. We can see that because the molecules are permanently color-coded. So these molecules that have, that are polar, sorry, I misread that. Molecules that are polar have a permanent dipole, not a temporary dipole, a permanent one. Experience dipole-dipole interactions. Is there going to be a bonus point assignment for this exam? Yes, there will be. There will be. I was going to get to that Thursday, and there will be. It's going to be on the gas laws. Okay, a 5-point bonus opportunity again. All right. Okay. So molecules that are polar experience dipole interactions. So the interaction, I'm going to use black right here, occurs between the negative and the positive regions. Okay, so if you have a whole bunch of molecules that they'll orient themselves this way, because just that's how like magnets orient themselves in a certain way because there's attraction there. That's where the dipole interaction happens. Right? So the positive pole of one molecule is attracted to the negative pole of another. And that is what creates the dipole interaction. So they are stronger than London dispersion forces, but weaker than hydrogen bonding. And I want to illustrate just how much stronger, like the impact of molecules that have dipole interactions, how that can impact molecules compared to other molecules that are just nonpolar. So this is, again, a figure straight from your textbook. We've got butane, okay, and acetone. Butane and acetone. So butane is C4H10. Acetone is C3H6O. Now, what's interesting, what I want to point out is their molecular weight. I'm going to zoom in for a second. I'll zoom back out. Look at their molecular weight, 58 AMUs. They weigh the same, the exact same. They have different elements involved, but they weigh the same. They're kind of the same size, in other words. Same size molecule. Arranged a little differently, but same size. But look at their boiling point. For butane, it boils at a very, very low temperature, negative 0.5 degrees Celsius. Okay, you don't have to apply any effort or hardly any heat compared to acetone. So here's the differences. Butane is not color-coded the way acetone is. Butane is a nonpolar molecule, entirely nonpolar. So the strongest kind of force that could happen between two butane molecules are just London dispersion forces, right? But acetone has this oxygen in it. This is the oxygen molecule right there. And so because of that, we can assign partial positives down here where the hydrogens are and partial negative up here where the oxygen is, because this oxygen is going to have lone pairs on it. We know that. All right. So there's a lot of electron density up here. So there's a dipole. We could draw that in pointing towards the oxygen. So molecules of acetone are going to orient themselves like this up here. The positive pole of one molecule is going to be lined up with the negative pole of the next one, the neighboring one. And you're going to get these dipole interactions between the molecules, okay? And it costs energy to break those apart, just like a chemical bond. So that's why these things have higher boiling points and higher melting points. Look, the difference is over 50 degrees. Okay, that's a significant difference. All right. Questions on dipole. So how do you know if a molecule can experience or have a dipole interaction?
It has a permanent polar like bond thing.
Polar. If it's polar and it has a permanent, yeah, dipole. Permanent separation of charge. That's what a dipole is. All right, any questions on van der Waals or dipoles so far? We're going to put this into practice in a minute. We're going to move on to hydrogen bonding. Okay, this is the king of all intermolecular forces. And as I mentioned, it's kind of responsible for why we have life on Earth. It's responsible for why water is a liquid at Earth's livable temperatures and not a gas or something like that, or a solid. It's the strongest intermolecular force. And then in bold, here's the actual definition of what a hydrogen bond is. It occurs between the lone pair on an oxygen, nitrogen, or fluorine. Okay, Molly mentioned that in the chat earlier, FON, oxygen, nitrogen, only the lone pairs on this, not a lone pair on a chlorine, not a lone pair on a bromine, not a lone pair on a phosphorus, okay? Just on oxygen, nitrogen, or fluorine. And a positively polarized hydrogen. What does that mean? It's just the hydrogen's got a partial positive charge on it. Okay, a positively polarized hydrogen is just one that has that. Okay, it's a semi-partial positive. So it occurs between the lone pair on oxygen, nitrogen, fluorine, and a partially polarized hydrogen, which is bonded to another oxygen, nitrogen, or fluorine. This is kind of confusing. Let's write out what this is. But first, before I do that, hydrogen bonding, somebody check that you're on mute. I'm getting a little feedback somewhere. Look at DNA. Okay, we know DNA is really important for many, many reasons. Look at the structure of DNA. We know it's a double helix. So you see this helix, you see all these little dotted red lines here that are connecting what? What are they connecting? They're connecting oxygens and hydrogens all throughout DNA. I mean, look at all these, all throughout DNA. I'll erase this one, include the oxygen, hydrogen. Okay, so what that must mean is that these hydrogens are positively polarized. And then we don't see it, but we know that there are lone pairs on these oxygens, okay? And those lone pairs make this oxygen partial negative. So that's where the hydrogen bond is at play, okay? It's just a very specific type of, it's kind of like a dipole, but it's a very specific type of dipole. So specific that we give it its own name, hydrogen bonding, because a hydrogen has to be involved, okay? You can't have hydrogen bonding without a hydrogen. All right, these dotted lines down here, don't get confused by that. That's just kind of showing you the hydrogen sticking out backwards. It's not a hydrogen bond, okay? Only the hydrogen bonds are the only ones dotted red in DNA. So it's at play in DNA. And then look, in a water molecule, this is a picture of a bunch of water molecules. The oxygens are in red, the hydrogens are in white. And you just see across a sea of water molecules, just a whole web of hydrogen bonds, all the dotted lines, okay? So they're always at play, specifically within water molecules a ton. So I wanna look at this definition in two specific molecules. I wanna look at water, and I also wanna look at ammonia. This is a figure from your textbook. I'm gonna look at water and ammonia. Both molecules, excuse me, water and ammonia, not ammonium, ammonia, experience hydrogen bonding between themselves, between identical molecules, okay? So two water molecules and two molecules of ammonia. So water, I want to label a few parts. We got the oxygen and we see the partial negative on the oxygen. We see the partial positive on the hydrogen, okay? These, a hydrogen oxygen bond, if you go do the electronegativity difference, that is a polar bond, okay? These are always polar bonds. So that's why we can write this separation of charge, the partial positive and the partial negative. Now, when we line up a hydrogen from one water molecule, remember these are forces between two molecules, so they're not within a molecule, it's between two neighboring molecules. When we line two up together, this partial, I'm just gonna erase this little line and I wanna highlight. This partial negative and partial positive right here, they see one another and they're attracted to one another, okay? And they form a temporary bond, okay? That's the hydrogen bond. But it's so specific, we label different parts of the hydrogen bond. We say the hydrogen is donating its electrons, any electron density or electron negative charge that it has, it's gonna be the donor. It's donating that to the oxygen, which is the acceptor. Okay, so any electron negative charge associated with that hydrogen atom is being pulled towards, the electron density is being pulled towards this oxygen, okay? And so that's why we call the hydrogen the donor. That's why we call the lone pair or the oxygen that has the lone pairs, that atom, the acceptor. So you always have to have a donor and an acceptor to have a hydrogen bond, okay? The hydrogen will always be the donor. It's kind of getting rid of some electron negative charge. and that is attracted to the oxygen, okay? Because oxygens are very electronegative. Remember, elements that are closer to fluorine on the periodic table, fluorine's the highest. The elements that are close to fluorine are very electronegative. They like to have electrons around them. All right, I want you to label the donor and the acceptor in ammonia. Spend a minute, just like we did on hydrogen here, label which one's the donor, which one's the acceptor between that dotted line, which is the hydrogen bond of nitrogen and hydrogen. What did y'all, anybody do it? Anybody label it? So in ammonia, you got NH3. And we see this dotted red line between this hydrogen right here and this nitrogen, the lone pair on that nitrogen right there. So which one is the donor? Thank you, Kylie. This is the donor. Yep, in the chat. So the hydrogen will always be the donor. And the nitrogen is always the acceptor. Okay, you got it, Molly? Okay, good. So on next week's lab, after the exam, don't think about this after the exam, but you're going to have to label donors and acceptors, or at least be able to count how many donors and acceptors. So if we're looking at a molecule of ammonia, just one NH3 here, like I'm just going to highlight the one I want you to think about, this right here. How many donors and how many acceptors are in one molecule of ammonia? How many total donors? You see the hydrogen bond just between this one hydrogen and the nitrogen.
None?
So what was that, Bailey?
In just one molecule of it,
In just one NH3, how many donors, how many acceptors?
right? Aren't there none? Isn't it just between the molecules themselves? Like, or not the like
Well,
when they share?
how many of these hydrogens could be donors is I guess what I should ask.
3.
Yeah, all three of them could be, because you know what? These nitrogen hydrogen bonds, these are all polar. So all of these hydrogens right here could be positive. We aren't showing all three, but all three could be. So you've got 3 potential donors here. And how many acceptors in this one molecule of nitrogen or ammonia?
1.
Yep, just one acceptor, and it's right here. This could also be an acceptor for another hydrogen bond. I'm just showing the example for one between these 2 neighboring molecules, but any one of these hydrogen bonds could be a donor, a potential donor. Okay. So in this one molecule, you have 3 donors and 1 acceptor. Does that make sense? You're gonna have to do stuff similar to this on your lab. Identify which atoms could be donors, which atoms could be acceptors. Okay. All right, so that's hydrogen bonding. Other things that I want to point out about hydrogen bonding. So based on this definition right here, occurs between lone pairs on oxygen, nitrogen, fluorine, and positive polarized hydrogen. Here's what that means. Obviously, we've got oxygen, nitrogen, fluorine. We know that fluorine, I want to move it down a little bit. Oxygen has 2 lone pairs. Nitrogen just is going to have 1 lone pair. We know fluorine has 3 different lone pairs on it. In the chat, let me catch up. So hydrogen will always be the donor, no matter what. Yes, you're good. So the hydrogen bond can occur between those lone pairs and a hydrogen that is bonded to another atom. I'm going to put an X here because X has to be oxygen, nitrogen, or fluorine. Okay. It's got to be a positively polarized hydrogen. Okay, so if X was carbon, then you don't get a hydrogen bond, okay? If this atom was carbon, then that hydrogen's not positively polarized because it's not a polar bond, okay, based on electronegativity differences. I know I'm not sitting here and adding those out or subtracting those out, but we said carbon-hydrogen bonds are never polar. Or if X is, again, you just have to look at the chart, but if it's not a positively polarized hydrogen, you don't get the hydrogen bond, okay? So there's 2 different ways that hydrogen bonds, I guess, could happen that I want to differentiate real quick. You have molecules that have both donor and acceptors can hydrogen bond with themselves. Okay, so for example, water and ammonia, they had both a donor and an acceptor, right? We labeled that on the molecule. But some molecules may only have one, like a donor or an acceptor. Okay, so I want to talk about those for a second. Molecules that have donor or acceptor, they can hydrogen bond, but not with an identical molecule, not with a molecule just like itself. So not with, I'm going to say not with itself. Okay, it would have to hydrogen bond with another molecule, like a water molecule or something that could provide the missing piece. Does that make sense? So what would an example of a molecule like that be? Well, HCl. HCl is an example because this is a polar bond. So this hydrogen is positively polarized. But the chlorine, those lone pairs don't count. It's got to be oxygen, nitrogen, and fluorine. So HCl could hydrogen bond with water, okay, a water molecule, because that oxygen could be the acceptor. You got the donor right here. This is the donor. But you don't have an acceptor. So it would have to hydrogen bond with another molecule that could provide the acceptors. That makes sense? Whereas molecules like water and NH3, these are examples of molecules that can hydrogen bond with another molecule just like itself. Okay, so again, you got to have both the donor and the acceptor. But if you have one or the other, you still can hydrogen bond. You just got to have a hydrogen bond with a molecule that's providing the missing piece. Okay. Questions on this so far? All right, we're going to start doing some practice now. And then I got a poll question here in just a minute. All right. So here's the first question. What characteristic or what kind of compound or molecule do you have to be to experience the following intermolecular forces? I should kind of reword this. For the interaction described to be the strongest. So for like if your molecule and London dispersion forces are the strongest type of force you experience, what kind of molecule are you? Molly in the chat says non-polar, and she's correct. You got to be a non-polar. Okay, so for London dispersion forces to be the strongest thing that you can interact with, you're a non-polar molecule. That's what kind of characteristic is what I mean. Okay, what about dipole-dipole forces? If that's the strongest kind of intermolecular force you can experience, what kind of a molecule are you? Chelsea said it, polar. And if you can hydrogen bond, yeah, Molly said polar without being dipole. That's very specific. Polar, and you don't have what it requires to form a hydrogen bond. That's exactly right. Now, if you're going to hydrogen bond, then what kind of characteristics do you have to have? You specifically have to have two things. Anybody? What do you have to have? What's one thing you have to hydrogen bond? Lucas says hydrogen, but not just any hydrogen, like Lucas. CH4, these have hydrogens all over it, but you cannot hydrogen bond here. So you can't just have hydrogen. You have to have a hydrogen that's positively polarized, okay? You have to have a hydrogen that's in a polar bond. So I'm just gonna write this. You have to have a hydrogen that is positively polarized because it's in a polar bond. And that's the donor. So you could tell me donor and acceptor, I would know what you mean, but you better know what you mean if you say donor and acceptor. And then you have to have an oxygen, a nitrogen, fluorine. Specifically, what we care about are the lone pairs there. Okay, those two requirements. So these are the acceptors. All right. Okay, next question. Identify the predominant or the dominant intermolecular force in each of the following substances. Okay, let's look at these. We're gonna do A, B, and C because I have a poll question, I think, on D, E, and F. So nitrogen, a molecule of nitrogen. First thing, let's just draw the Lewis structure. That's gonna help us see what we have. We've got nitrogen, triple bonded. You had to draw this Lewis structure on your homework. I got emails about this question too. Triple bonded to nitrogen. We got lone pairs. Okay, now we're just talking about the pure substance here. Okay, the pure substance, like just nitrogen, not nitrogen and a water molecule, just nitrogen. Okay, so if I had 2 molecules of nitrogen, what type of intermolecular force would these 2 molecules experience? The strongest one. Kylie says London dispersion. Why is that?
It's non-polar.
That's exactly right. Non-polar molecule. When you have 2 identical atoms bonded together, those bonds are non-polar, okay? So because it's non-polar, the strongest type of interaction we could have is London, I'm gonna abbreviate, London dispersion. Okay, you can write LD, you can write van der Waals if you want. London dispersion, van der Waals. Okay, HCN. HCN. Let's draw the Lewis structure for that. We got hydrogen bonded to a carbon. Carbon has to have 4 bonds, but we got a nitrogen, and nitrogen has to have 3 bonds, so we put a triple bond right there. And we have a lone pair. Okay, now here's what I see. We've got a hydrogen and we have a nitrogen with a lone pair. Could this thing hydrogen bond with another molecule just like it? Kristen's shaking her head no. Why? You're right.
Hydrogen is in a positive dipole.
This
thing.
bond right here exactly is not polar. So that hydrogen's not positively polarized. Okay, you can't draw the partial positive, partial negative on it. So again, if we just have 2 molecules of HCN, this is cyanide, what kind of intermolecular force would it experience though? Do we have anything that is it polar? Is it non-polar overall? What do you guys think? Some of you are like, I don't know, I need an electronegativity chart. Well, I put one here just for you. We got nitrogen and we got carbon bonded to each other. What's the difference between 3 and 2.5?
0.5.
0.5. And remember, if you're 0.5 or above, you're polar. So guess what? I'm going to highlight this bond right here. This is polar. We can draw the partial negative and the partial positive on the carbon. We could draw in the dipole. Boom. Okay. So this is going to experience, if you had 2 molecules, if you had another HCN, and you got the partial positive right there and the partial negative on that one, you're gonna get some dipole interaction right here. Okay, so this molecule is polar. That's why. Okay, last one we're gonna do before I run a poll question is C. I'm gonna come over here where I have some blank space. CCl4. So we're gonna draw the Lewis structure for CCl4. Okay, there we got it. If we have 2 identical molecules, CCl4, carbon tetrachloride, what type of interaction can these molecules experience? London dispersion, or van der Waals, dipole-dipole, or hydrogen bonding? You should be able to rule out one really quick. Can't hydrogen bond, right? Because you don't have hydrogens, and you don't have oxygen, nitrogen, or fluorine. So hydrogen bonding is out of the question here. Now you just have to decide, is this a polar molecule or is it non-polar? Any thoughts from anybody? Could you show us the electronegativity chart? Yeah. Molly says non-polar, so we got carbon and we got chlorine. And the difference there is 0.5. So every single one of those carbon-chlorine bonds is polar. But Molly, why did you say nonpolar overall? I agree with you.
It's just, I don't know, it's because it's symmetrical.
Yeah, you can draw
So-
dipoles in on every single one of these, pointing towards the chlorines. But here's what you should notice when you do that. There's symmetry, okay? So the left and the right dipoles cancel, the up and the down dipoles cancel. So overall, this molecule is non-polar. So that means if you had another identical molecule sitting right next to it, the type of interaction between these two molecules, the strongest that could be is London dispersion forces, because both molecules are nonpolar. In the chat, is it if it all points towards carbon, it's polar, and points out nonpolar? Yeah, if the dipoles are pointing opposite ways, then they cancel. If they're pointing towards each other, they do not cancel. So for example, the classic example I like to give is water molecules. Some people will draw water like this. Even though it's bent, the geometry is actually bent, you can draw those dipoles in pointing towards each other. Those don't cancel because they're both pointing the same direction. All the electron density is right there on that oxygen, okay? But if they're pointing opposite ways, like in that carbon tetrachloride, then they do cancel, okay? All right, I don't consider these problems to be all that simple because there's a lot of different nuances to these. These are like deciding if a molecule's polar all over again. All right, so I'm going to run a poll question because I want you to consider. I want to see how well this has sunk in on the next three. So I'm going to give you a couple minutes to do this. What is the dominant intermolecular force for ammonia, NH3? What is the dominant IMF, intermolecular force for CH3Cl? And then CH3COOH. So it's going to help you to what we've just done. If you were like, well, how do I do these? What did we just do? You draw out the Lewis structures, and then you assess if the molecules. I'm going to scroll down and keep the electronegativity chart visible. I think that should be good. You should be able to see it. All that you see from here. If you need to calculate an electronegativity difference real quick, do that. And then assess, do I have any symmetry or no? One of these molecules we've already talked about. So that one should be quick. Please have your video on with us if you can. It always helps. And do these problems with us. If you're just waiting for me to share the answer, you're not really challenging yourself right now to think. And that's what you need to be doing. Even if you're unsure, it's good to wrestle with these things on your own. All right. I'm starting to see some answers come in. I'm going to give it about 30 more seconds because then we will have spent about 3 minutes. And there's a few more things I want to get to. We're closing in on time before lecture's over. So go ahead and start putting your answers in. The first one should be real easy because we already talked about ammonia. I'm going to go ahead and start drawing the Lewis structures out for these things. I'm going to do them down here. There's ammonia. Methyl chloride and F. You got a carbon. Gonna have to double bond it to one oxygen and have an OH because it's the only way it's gonna work. So that's what your Lewis structure should look like. All right, I'm gonna end the poll. We're all at 81% voted, which is pretty good. Let's look at the answers. Okay, so for the first one, pretty much everybody, most people picked NH3, but we should have had 100% on this question. I don't know why we didn't have 100% people pick hydrogen bonding for NH3. Okay, why is that? Well, look what we have. Nitrogen, hydrogen, if you're doing the electronegativity difference, these are all polar bonds, okay? It's polar bond, so guess what? We got a partial positive here, and we got the partial negative here. We have a partially positive, partially polarized hydrogen, and we have a lone pair on this nitrogen. So if we're labeling, this hydrogen is the donor, and this lone pair, this nitrogen with the lone pair is the acceptor. We got a donor and acceptor. So this can hydrogen bond. Right? So we should have had 100% on that because we already said ammonia can hydrogen bond above. What is the dominant force for the next one? Most people said dipole-dipole. Okay, so we know that these bonds right here, all the hydrogen-carbon bonds, these are non-polar. But this carbon-chlorine bond is polar. So we have a dipole here. We can draw in the partial negative and partial positive on the carbon. You could draw on the dipole. It does not cancel. So the strongest force here would be dipole. Dipole-dipole. Right? You got a permanent dipole on that molecule. F, we've got carbons with hydrogens. None of those bonds are polar. We got a carbon-carbon bond. That's not a polar bond because two identical atoms. Then we have these carbon bonded to oxygen and an oxygen bonded to a hydrogen. So here's what I see. We got a positively polarized hydrogen right here. That oxygen on that hydrogen bonded to that oxygen is positively polarized. And we also have lone pairs on oxygens, which is both necessary elements for hydrogen bonding. So this is going to be the donor. These lone pairs, any of these lone pairs, we got 4 different lone pairs. Each one of these could participate in a hydrogen bond. So how many acceptors do we have on one molecule? We're going to write A for acceptor. Okay. We got 4 different acceptors here. Just one donor, but 4 different acceptors. All right, so this for sure can hydrogen bond. All right, that's the strongest. That's the strongest intermolecular force at play here. All right, questions on what we just did. I'm going to stop sharing. Most people pick dipole-dipole for number 3. It could experience dipole forces, but the question was, which is the strongest intermolecular force? And the strongest that it could experience is hydrogen bonding. Okay. Gabby says in the chat, how do you know what the donor is? It's always the positively polarized hydrogen. That's the one that's always going to be donating electron density to a neighboring oxygen, nitrogen, or fluorine. Does that make sense, Gabby? It will always be the hydrogen, the positively polarized hydrogen. Abby said, I know you said this, but I think I missed it. Each lone pair can be an acceptor, correct? Yep, that's why we labeled A on all of those lone pairs on all the oxygens, Abby. Very welcome. Okay, we're closing in on time here. We got about 10 minutes left. I think I left a blank slide for review, but this is a question I'm going to go over probably in a review. Okay, but it's a great question if you want to look at it ahead of time. In the chat. So on dipole-dipole, the positive overrules. Maya, help me. What do you mean exactly? So like when you draw in, let me scroll back up to this molecule. We could draw in the partial positive and partial negative. You can draw in this permanent dipole. If you can draw this in, that's how you know you get dipole-dipole. And if you don't have the necessary requirements for hydrogen bonding, like you don't have a donor and an acceptor on the same molecule, it can't hydrogen bond with itself. Does that help? Okay. Bailey says, will the redo homework open today? Yes, it will. I'm going to do that right after this lecture on my office hour. And Pernell says, so acceptors are negative with lone pairs and donors are the positive hydrogen. That's exactly correct, Pernell. Exactly correct. Okay, these are not easy questions. There's a lot of stuff to consider on these, okay? Like I said, this is a great practice problem. Which can hydrogen bond in its pure form? That would mean two identical molecules. Which one could hydrogen bond, not with itself, but maybe with a water molecule? So there I'm asking, which molecule has both a donor and an acceptor? Which one maybe just has one, a donor or an acceptor? Okay. So maybe consider that question. I'm going to look at it on the review before the exam. I'm going to skip over this. This table right here is just a review. Everything we just talked about all in one little table. And because for time's sake, ignore this table here. Sometimes I make a point about it. I never really ask anything about it on the exam. So that's not going to be anything to do with that table on the exam. So let's move on. I'm going to introduce gases and gas laws. And then I'm going to also tell you about the bonus point opportunity for, well, yeah, I'm going to try to tell that in the next 10 minutes. Okay, gases. We're going to talk specific. We've been talking about gases, liquids, and solids and the type of forces that can exist between these three different states, right? Now we're just going to really hone in on gases. So the rest of the chapter, we're just going to be talking about gases and their behavior and how we can model that with equations, okay? But before we get there, the three properties we can use to characterize gases are pressure, volume, temperature, right? Pressure, volume, and temperature. I got this picture here of these cylinders. Anybody know what these cylinders are? Sometimes you see trucks going down the interstate. I always get really nervous when I see those specific kinds of big trucks hauling cylinders like this. What's in these cylinders? Anybody know? A lot of times you see these in research labs. Gabby says protein, oxygen. Well, I don't know what exactly kind of gas is in these unless you read the labels, but it's a very highly pressurized gas, okay, a compressed gas, because there's space between gas particles, right? So you can compress them down into containers, small containers. The only issue is like think about a helium tank, okay? What happens when you open the nozzle on like a helium tank if you're gonna blow up a balloon? Or an air compressor, anybody ever dealt with an air compressor? My husband had one in our house last night because we're redoing our bathrooms. So much fun. And what happens, the gas comes out really, really high and fast volume, right? It's so loud. Yeah, they're super loud. So anyways, you can compress gases. The issue is though, gas particles still have high energy. So the reason these are so dangerous, like the reason you see them literally chained to a wall, is because if something were to happen to these and they kind of explode for some reason, if you heat them up, never put a flame or heat near compressed gas tanks. If you see that, run. These could literally explode through concrete walls, okay? Because sometimes the gas is so highly pressurized, like 2,000 pounds per square inch, right? That it would just explode if there was a leak or something or heat that caused them to break the canister. So anyways, what is pressure? We're talking about pressurized gas. Why is there so much pressure in these things? Well, pressure is just a force per unit area, all right? You're probably most familiar with this with the tire pressure. Anybody ever have a flat tire or your tire pressure's low? How many of you? I was always thankful when I'm gonna travel, my dad's like, your tire's low, I need to fill it up for you. I'm thankful for the people in my life who think about my tire pressure because I don't. But why do we have tire pressure? Well, we have gas, air in our tires, and those gas particles are constantly hitting the walls of the tire, and that creates pressure on our tires. It keeps them inflated. Somehow, I got a scissor in my tire a few weeks ago. Wow, Bailey, that's a new one. I've never heard that before. All right. So tire pressure is often measured in PSI. Okay, anybody have a little instrument that can gauge what your tire pressure is? PSI, which stands for pounds of pressure, that's the force, per square inch. That's the area, square inch, right? So pounds of the force, square inch of the area, abbreviated PSI. So this is 1 unit for pressure. Now, I'm going to tell you, I hate pressure for this reason. There's so many different units for pressure. I don't know why there are so many different units. I wish there were not units like this for pressure, but there are, and you need to be familiar with them because you're going to run into this maybe the further you go in health science fields. Okay, so pressure. There's another unit of pressure I'm going to introduce to you. The air in the atmosphere above you. Guess what? It puts pressure on you. You thought it was your chemistry class. You thought it was Chem 1402 putting all this pressure on you, stressing you out, making you worry. It's not. It's the atmosphere, okay? It's literally, look, 14.7 pounds. You go pick up a 15-pound weight. That's how much pressure is on you from the atmosphere at all times. Now, we've lived with it. We're used to it. We don't necessarily feel it. Sorry, I got distracted in the chat. You ran over a muffler on the interstate because you thought it was a rain boot? Wow. Tire problems, okay? All right, so anyways, this is another unit of pressure, okay? 1 ATM equals 14.7 PSI. I tell you the one thing, I'll run over almost anything, but I do not want to run over a possum. Guys, one time it almost happened, and possums are just like the grossest, I think they're like the grossest animals in the world, okay? So if you have a funny story about running over something, yeah, that does not sound good, Rachel. Armadillo, sorry, close a second. I have a terrible story about an armadillo. My husband killed them with a shovel in our backyard one time. They carry like diseases, okay? So you really can't let them, like, this armadillo was not changing its mind. It was like headed straight towards us, and he had to kill it. It was, I don't want to think about it anymore. Back to pressure. So 1 ATM, this is atmospheres, ATM, okay? Atmospheres equals 14.7 PSI at sea level, all right? So at sea level, if you're standing at sea level, I fortunately got to go to Colorado over spring break. We were 12,000 feet up, okay? So obviously the higher up you climb in elevation, or if you're in an airplane, the lower the atmospheric pressure, but at sea level, 1 ATM equals 14.7 PSI. All right, let me introduce another unit of pressure. Oh gosh, we got 4 minutes. I'm gonna introduce this last one and then I'm done. I'm gonna tell you about the bonus opportunity. This is derived from a more technical chemistry instrument. Y'all are all kinds of stuff in the chat. I can't read it now. I'm gonna get distracted and laugh. This is a chemistry instrument. This is called a barometer. All right, it's a dish that has mercury in it. And the fun stuff here, so atmospheric pressure pushes down on the mercury and it causes it to shoot up this little tube. And they measured it, and the height that it climbed in the tube, I know, real riveting, was 760 millimeters. That's how tall it went. Okay, so if atmospheric pressure is pushing down, it climbed up. So this is a whole unit of pressure. I know. It's like, do people not have anything better to do with their time but to come up with units of pressure? Millimeters of mercury, okay? Sometimes it's called a torr based on the guy who spent the time to do this, all right? So 760 millimeters of mercury equals 1 torr equals 1 ATM, all right? All right, that's all the units of pressure we're gonna do today. So we got millimeters of mercury. You might have actually been familiar with this unit before, millimeters of mercury, or inches of mercury sometimes is another one you'll see. ATM and PSI. And then we're gonna learn how to do conversions with these Thursday, and we're really gonna dive into the gas laws more on Thursday. So that brings me to, I'm gonna keep my screen up for a second, but I wanna tell you about the bonus point opportunity. Okay, I'm gonna post a new discussion board thread, and it's gonna have very specific instructions, okay? So if I don't explain it very well right now, I'm gonna get this posted today. So you're gonna have a whole week, pretty much. It'll be due probably the night before the exam is when it's gonna be due, if you want an opportunity for bonus points. Gas laws. Okay, so we got, maybe you've heard of these in a science class before. How many of you heard of Boyle's law, Charles' law, Gay-Lussac's law? Okay, or maybe even the ideal gas law. I want you to pick one of those laws. Again, I'm going to post all the instructions for this on the discussion board thread, but you're going to pick a gas law, and I want you to tell me how it relates to your area of health science. I had so many creative ideas and thoughts from people last semester. You need to research it, okay? So you can find an article, you can find something on the internet. Okay, you can link me to an article. You can tell me if it's in a book. You read about it in a book. We're actually going to work a problem with Boyle's law on Thursday. With people who have like a collapsed lung and they're being like flown to emergency room, about how Boyle's law is at play with like patients being put in like helicopters and things. It's gonna be really cool. So it does relate, I promise. Now, if you're like